All right, so today we're doing 4.1 extreme values of a function. So we've talked a little bit, I think, about this. I can't remember at this point in the year, actually. So we have an absolute max and absolute min. So by definition, um, we have it if the one value is less than the other value. So, I mean, it's back from like algebra when you would do absolutes and stuff. So if you remember from pre-calc, I'm going to put a little picture here. So I have something like this. This right here would be a max. This is called the absolute max because there's no point higher than it on the graph. And then down here, when it says local, this right here would be a local or a relative, depending on which book you use, a relative max. And then this point right here would be called a local or a relative min. So the reason it's only a local is because the points around it are lower than it, but this point over here is definitely lower than that point. So that's why it's not the absolute. So for absolute, it has to be bigger than every other point. So if I had something like this and they're the exact same height, that would not be absolute. They both would be considered local maxes in those cases. So the way we figure out this mathematically, if something is a max and a min, is by taking a derivative equaling it to zero. Because, right, this is a slope of zero, slope of zero, slope of zero. So to figure out where max and min happens, we take a derivative, equal it to zero. The derivative could also be undefined because if we did something like this, that's still an absolute minimum value here. But the derivative wouldn't exist at this point. So we still check for the d/e's. When you take the derivative and you equal it to zero, that right here is called your critical point. All the other definitions I gave are up here too. So derivative equal to zero, critical points. So what we're going to do is we would test it just to make sure. So if we took the derivative equal to zero, this sign chart should say positive, negative. So it's going up and then going down. Like this one here would go negative and then positive because it's going down and then it's going back up. So I'm going to show you algebraically what these type of things look like. So define an absolute max or min on this. So I gave you a closed interval. So in a closed interval, you must check the endpoints. In the AP exam, they always give you they give you endpoints, and you have to check it because sometimes those points are actually the max or the min. So it'd be like this picture right here, and what they do is they cut it off right there. So you found a minimum, but this point was actually lower than that one. So you have to check the endpoint to see if it's lower than the other points that you found in the interval. So this right here, if you took the derivative, so the steps to find the mins would be take your derivative, and then where does this equal zero? So this is zero nowhere, but it's undefined at zero. So we'd have to still check zero. So you'd have -2, 0, and 3 on here. And so it was like what we were doing when we were talking about our particle. That's what we were doing, talking about our particles moving left and right. So it's the same idea. So you plug in a number. So plug in -1 into the derivative here. That comes out negative. Plug in 1 into the derivative. That's positive. So that means 0 would be your absolute, we'd have an absolute min here. So what this is telling me is that my function is going down and back up. So there's no point that could possibly be lower than it. And then if it wanted the maximum, we'd have to check at -2 and at 3 to see what these y values are. So you plug in -2 into the original. So you'd have like -2 squared in the cube root, and you plug 3 into the original. And whichever one of those has a higher y value, that would be your maximum. So it ends up being x equals 3 would be your absolute max. So really what we did is we cut it off closer up there. And this is not a parabola. I just drew a picture of the derivative, not of the original picture. So here is just a bunch of practice. All we're going to do is practice taking derivatives, equaling them to 0, and solving them. So what I'm going to do is I'm actually going to put on a separate sheet of paper because I don't have enough room on here. So number 1, I'll put it up here. So take the derivative of this. That would be x to a -1. So the derivative would be -x to a -2. Derivative of ln is 1 over x times 1. So then this would be x to a -1. So pull out the smaller number, so x to a -2. And if I divide that by x to a -2, that gives me plus an x. So then this is equaling 0. So it's undefined at 0. And then it's this is equal 0. So that's at 0, and this is at 1. I would not test 0, though, because 0 is not defined in the original function. 1 over 0 does not exist, so I cannot test it. Does that make sense? So if it's not in the domain of the original function, you do not test it. It cannot be a point that was a max or a min. Now it can be undefined in the derivative, and that's what I showed you, like an absolute value, the derivative would not exist. All right, so we only have to test the 1, and then we're going to test these endpoints also. So you test your 0.5, and then my 1, and then my 4. So you do your sign chart. So if I plug in, like, see, 3, positive, plug in like 0.75, that would be a negative. All right, so then it's like the one we did before, where you would test your values. So I need you to plug in your values. When I plugged in 4 into the original function up here, I have 1 over 4 plus ln of 4. Says 1/4 plus ln of 4. And then plug in the 0.5. So 0.5 gave me 2 minus ln of 2. And ln of 2 is the same thing, you guys. If I have ln of 1/2, you have to remember, like, this is a trick they do in AP all the time. So that's really ln of 2 to a negative 1, right? Because 1/2 is just 2 to a negative 1. And remember, exponents always come out in front. So it's also equal to negative ln of 2. So that's all I did right here. And then I plug in 1 into the original, and I get 1 out. So then I would figure out which one of these are. So this right here is the minimum. And then this one would be the absolute max on the interval because it was higher. I'm adding something to it. And then this right here is my local maximum. And then this right here would be the absolute minimum. All right, so for number 2, just take your derivative. I'm going to move that out of the way. So the derivative of that function, what is it, is going to be 4x minus 8, equal that to 0. I get x equals 2. There's no interval, so all I have to do is check the 2. So if I plug in 1, it comes out negative. Plug in 3, positive. So all I have here is an absolute min, and it's at 2 comma whatever the y value would be. I think it's 1, if I can read my handwriting correctly. The reason I know it's absolute is because this function goes down and back up. So there's not some trick like this is always going to be this and this and that. You just have to look at the sign chart and what does the graph look like. So that one would be an absolute. I'm going to go to number 3 over here, and then I might skip 4. For right now, we can do it in class if we need to. I don't think I can give you anything that hard. So the derivative of this one would be cosine of x. So I need to figure out where that equals 0 at. So that's going to equal 0. Let's see, cosine equals 0. That's the x value. So that's at pi over 2 and 3 pi over 2. And it's from 7, so that would be in there. But I have to minus off pi from it. So that gives me pi over 4 is a 0, and 5 pi over 4. And then I'm going to use the endpoints that they gave me also. So I have a 0 and a 7 pi over 4 on my number line. So I just need to test all my points. So let's see if I plug in something inside of here. Cosine's positive, cosine's negative, and then cosine would be positive, that last interval there. So then that tells me that this is a possible max. That's a possible min. I also have to draw these pictures. So it's going up. So 0 is a possible min. And then it goes up and then down and then back up. So then this is also a possible maximum. So then I just plug in the y values to see which one is which. So I get 0 was 1 over square root of 2. And then when I plugged in pi over 4, I got out 1. 5 pi over 4, I get out negative 1. And I'm actually just plugging these values into the original. So I'm doing sine of 0 plus pi over 4. So it's sine of pi over 4. So this is really the same thing as radical 2 over 2. That's typically how I used to write it. And then my last one is 7 pi over 4. I get out 0. So then this would be called my local min. This right here would be my max. This would be called our absolute max. This would be called my absolute min. And then this right here would be a local max on the problem. I want to get over to one of the square roots or so on it. So I get number 6. Let's get to I guess I'll do 4 real quick for you, since it's just me doing them. So the derivative of that, so then that just gives me x over the square root of x squared minus 1. So then my 0 would be 0. The bottom would be 0 at plus and minus 1. So I had to check all of those. So I have negative 1, 0, and 1. And these are defined in the original, so that's why I'm allowed to check them. And so when I plug in into here, I plug in negative a half. Negative a half. Oh, it's not going to be defined inside of there, though. So I could plug in like 2 and bigger. So in between here, it's not defined. So it must be a function that looks like this. Something like that. So I can't test in the middle. So 0 is not actually going to give me anything because it's not defined on the original. I just saw that. You see right here, if I plug in 0, square root of negative 1 doesn't exist. So 0 is not really in the domain. So we're just checking negative 1 and 1. So when I plug in like negative 2, that'd be a negative. So that's a negative. And then plug in 2, that would be a positive. That tells me that my picture does look like this. So it's going down and then coming up. So these are both possible mins. So I would put in the values and I get out 0 each time. So negative 1, 0, and 1, 0 would both be local mins. So they're same y values, so you would not say absolute on that problem. All right, let me look at number 6 now in your guys' notes. So the derivative of this would look like that. So this gives me a 2x squared. So that gives me So if I set that equal to 0, I'm getting x squared equals 1, so x equals plus or minus 1. And that works in the original, so that's good. The bottom will not ever be undefined because that's not going to ever equal 0 for me. So I just need to check negative 1 and 1. So I plug in 0. I get 1 over 1. 2. Plug in negative 2. So my function is going decreasing, increasing, decreasing. So there's no domain, like I didn't put anything, it's not closed over here. So you see how these two, I had intervals I had to test. These don't have intervals, so it's just going like this. So this is going to be my min, that's going to be my max. So I plug in negative 1. Apparently I have not plugged in negative 1 yet on my answer key. So let's see, you get, that's 2, so I get negative a half. And then I plug in 1, and then get 1 over 2. So then this right here is my local min, and this is my local max on the function. Let's see what the back says. So I talked about looking at graphs and seeing and whatnot. Oh, the intermediate value theorem I should have said something about. So we've talked about the intermediate value theorem before, but intermediate value theorem, first it has to be a continuous function on a closed interval. So if the interval is not closed, then the theorem does not apply. Does not mean that you won't have a max and min. It just means that you're not guaranteed a max or min. So what it's saying is if you have a closed interval, then there must be a max and there must be a min on the interval. So it's continuous and closed. So I have a function, and no matter how I look at it, as long as these endpoints are closed, there must be a max and a min in there. Even if we have it a closed interval on there, we'd have the functions, and it was continuous. So on the back, it was just asking you, could you use the mean value theorem? So you can't use it here because it's open. That's not continuous. Like they're not continuous on the intervals here because they all have open dots. You still can have max or min. See, so there's a max, there's a min. Right here would be your minimum value. I think this one's filled in here, and this one's filled in. So you'd have 2 local mins here, and that one's open. I think that one's closed. So that one right there could be a local max. I guess it would actually be absolute in this picture because there's nothing higher than it because that one's not filled in. So hopefully we can talk about it some more tomorrow. If you guys have questions, shoot me emails if you have anything that you don't understand on this. So your idea should be taking derivatives equal to 0 and testing your function.